All right, good morning. Happy Monday. This week we're going to be doing even more jumping around than I thought we would. You may recall last week we were going to go into AVL trees, and then I decided to skip that and go to heaps first because I need more time to revise the slides. That's taken care of. There was something that looked like a typo that made me doubt everything that I've ever known, but nope, turns out it's right. We're all fine. I could, hypothetically, go back to AVL trees right now, but I want to jump around slightly less than that. Instead, we're going to finish the latter half of this week's slide first, the ones to do with the heaps. But that will only take us like half-ish way through our discussion on heaps. Next week's topics, and these slides are already available on LearnLearn, next week is entitled Heaps and Graphs. So we're going to start by continuing the heaps part of AVL trees and heaps. Then we're going to skip the next week's slides, do the heaps part of heaps and graphs. Then we're going to go back to this week's slides, do the AVL trees stuff, and then talk about graphs. Just back and forth and back and forth. So let's get started on heaps again. We left off last week talking about how heaps are stored. Heaps are generally stored in arrays, while trees in general use a linked data structure similar to what you saw in the assignment. Speaking of assignments, I totally forgot to go over the assignment 3 answer key in class. I'll go over that this Friday. Anyway, we use arrays rather than the usual linked structure. And I kind of sort of justified why, but we're going to talk about that in more detail today. So one nice aspect of the array structure for this is that the first index of the array, position 0, is always the largest entry in the heap. Heaps are sort of specialized to be able to get the largest entry of a data set really quickly, with the trade-off of other operations not really making sense to do. And then we can also do some quick calculations to get the children and parents of any entry in the array. So here's something to think about. Given an index of a data item, where might its left child, right child, and parent be? So in this example, we have the root at index 0, and then its children happen to be at indices 1 and 2. And then its children are in 3, 4, 5, 6, and so on. So we might be able to figure out a pattern of where these children are stored. It seems like if we want to find the child of 60, we just go to the next node and the one after that. But then to find the child of 57, that is a tiny bit farther in the array. Nothing to worry about yet, though. Hello? And then 45 is connected to the sort of next chunk of the array. And this will keep going. The children of, left child of 52 is 42, and that is after the or the first node after all of its siblings. And you might notice we're skipping forward a power or a multiple of 2 each time. No, a power of 2. There's 1 node on the first level, 2 nodes on the second level, 4 nodes on the next, then 8 and 16. Actually, I'm going to keep this one. So the general formula for this, it turns out, is that for any given index, you can get the left child of the node at that index from index 2i plus 1. So let's find the left child of 42. That's at index 1, 2, 3, 4, 5, 6, 7, 8. Then 2 times 8 plus 1 is 17. 8, 9, 10, wait, 0, 1, 2. Haha. Forgot we were counting from 0. Anyway, 7 times 2 plus 1 is 15. So 7, 8, 9, 12, 13, 14, 15. And is this right? Where is 42 anyway? Yaha! Left child of 42 is 16. Likewise, the right child, because of the ordering we're using, is right next to the right child, right next to the left child, I mean. So it is at index 2i plus 2. So again, 42 is at index 17. No, 42 is at index 7. 7 times 2 plus 2 is 16. Over here, and that's consistent with what we see in the graph. So this isn't quite showing off an advantage of an array structure quite yet, but instead we see here that the structure of a perfect binary tree, remember that means that all of the levels except the last one are full, and all the nodes on the last level are as far to the left as possible. That kind of binary tree lets us use an array. And then from there, we can take advantage of the intrinsic benefits of arrays, namely faster speed. All comes down to speed. Last thing for this bit is that to get the parent of a node, you can do that calculation in reverse. You could do some algebra yourself to derive this, but the parent is stored at index floor of I minus 1 divided by 2. You can see it here. So let's try that again. Without looking at the graph itself, I want to find out what the parent of node 29 is. So that's at index 14, 13, 12. Minus 1 over 2 is 11 over 2. Which is 5.5. You got what I hope wasn't your introduction, but might have been an introduction to the floor function on assignment 2. We'll talk about that a tiny bit more. That function basically takes off the decimal portion of a number, rounds down to the nearest integer. So according to our calculations, the parent of 29 should be 30, and it sure is. Excellent. So here are those formulas again. They're probably pretty strange right now, but I assure you you'll get used to them pretty quickly. They feel intuitive, even though I remember going like, 5 plus 1, how did they get that? So now we'll talk about some operations. And also, we talked about this last week, so it might be discarded out of memory, but I want to keep in mind during this discussion that the heap is useful in that it can implement a priority queue, which has many practical applications like a queue for patients being treated at a hospital. So I don't want to get too bogged down in like, ooh, this is cool theory, look at all these calculations. We kind of sort of have a goal here. And the goal is to implement a priority queue with both insert and retrieve max operations being really quick. Because if you try and implement a priority queue with any of the data structures we know now, one of the two operations will be really slow. So, insert. Let's assume that the array we're storing the heap in has room for the new entry. That's just to avoid having to talk about allocating space for a new array, because that's not really important, losing sight of the actual data structure here. We're going to assume that there's like at least one empty space on that last row of the tree. We're going to insert an entry with priority 50. And the current size of the heap, we're going to call n. So there are n nodes currently in the heap. We start by adding the new entry in the next available position. In the array representation of this heap, this is going to mean that we put the new entry in the last entry of the array. The last open entry of the array, I should say. There are going to be free indices here and here as well. So you might get lucky and have it so the tree is already in heap order. Don't have to do anything else after this, but we are not that lucky. Recall that heap order is sort of like a more relaxed version of the binary search tree property. Rather than the nodes having to be in a super specific order, heap order just specifies that every node should be larger than its two parents. The rest of the heap is already in heap order, otherwise it wouldn't be a heap. You could see examples everywhere. 60 is greater than both 57 and 45. 48 is greater than both 20 and 25. Cool. 30 is greater than 28, but it's not greater than 50, last I checked. So we need to do some fixing up on the tree to make sure that, or to make it so the resulting heap is in heap order. We do this using a kind of sort of recursive operation. It's not really recursive, it just goes up the tree. You start at the node you just inserted. Check whether the parent priority is smaller than the new priority. And then we swap. guess a more general way to say this would be something like, if parent less than child, swap. And of course, we won't have convenient little variables for parent and child. Before we had pointers, but you'll learn in other classes that pointers are slow and array indices are way cooler. So just imagine instead of parent, you have something like A at index I minus 1 over 2 floor of that, and child you just have index I, whatever. We find that the parent is indeed less than the child, so we swap them. Now, we do the same thing with the entry we're inserting and its new parent. 45 is less than 50, so we do that swap again. And we keep going as far up the tree as we need to. Is 60 less than 50? No. It's fine. We don't have to make this swap, and you could probably prove this by induction or something, but who has time for that? Now that this entry, this new node we added, is in heap order, it's less than its parent and greater than all of its descendants, the entire heap is in heap order. This example almost showed the worst case runtime for this algorithm. The true worst case would have happened if we had a parent that was also less than the node we're inserting, and we had to do one more swap. But if that happened, the new node would be the greatest element of the tree, and there would be no more swaps possible. We would have a new root of the tree, no parent, nothing to check, we're done. As such, the insert operation, at worst, involves traversing a branch of the tree from the leaf to the root. And as discussed before, the height of the tree is in big O of log n, n being the number of nodes in the tree. And this makes it so the time complexity of the insert operation is also big O of log n. These implementation notes feel a bit obvious, whatever. In the code, all the checking and swapping is done using array indices. Like I mentioned before, my pseudocode example is massively simplified. You would have indices into the array A in place of parent and child, and an actual swapping algorithm in place of that swap function. Additionally, the heap has to keep track of its own size, so you have to increment it at some point. Cool. So let's draw a heap. We're going to insert a few entries with priorities given on screen, and just do all the necessary operations along the way. We start by adding 10. There's nothing we have to do now. I'm going to attempt to draw the array as well, in addition to the tree. I just got that idea now, so this might go terribly, but we'll see. So we got 1, 2, 3, 4, 5, 6, 7 things we need to keep track of. 0, 1, 2, 3, 4, 5, 6 array indices. And the first one will include 10. The second item we insert, 20, will go at the first available position. And then we check, is this in heap order? The magnitude of the parent should be greater than the child. This is not what's happening. So we're gonna swap them. And I'm also gonna draw the whole thing a bit smaller because I think I'm gonna need more space. All right, we have a heap so far. Now we put in 15. Goes in the first open spot in the perfect binary tree. And this is fine. 20 is greater than 15. It's still greater than 10. The whole thing is still in heap order. Now we insert 5. This is also just fine. But now we insert 25, and something looks very, very wrong. Yeah, 25 is like super greater than 10, also greater than 20. So we have some swapping to do.
Is there 35 that you had? I mean, not 25.
Oh, truly. I guess we still have the exact same situation, but still thanks for pointing that out. Do I have all the rest? 10, 20. Okay, yeah, we're good. Even though we're in deep, deep trouble right now. So 35 and 10. 35 is greater than 10, so we need to swap them. And notice this also has those array indexing calculations in action. 4 minus 1 over 2, floor that. Wow, it just works. The parent of the node at index 4 is at index 1. And what were we doing again? I think we put 35 right here and 10 there. We continue up the tree. We achieve our worst case of 35 needs to be swapped with 20. All right, now we insert 25. It goes here, I guess. This doesn't really look like a left child, but it is. Luckily, I have an excuse to redraw the tree because we need to do at least one swap. Oh, and 25 is here for now. So 25 is greater than 15. We gotta swap them. And last one, we're gonna insert 30. It'll go right here. And we need to do just one swap to replace it. Cool. As always, I don't make the quiz questions until Wednesday at the earliest-ish, but I probably just walked you through a quiz question. The answer key for which is right here. Looks good to me. And now for the heart of the heap data structure. The retrieve max operation. It's right here. I just retrieved it. But it's not that simple. We already know where the max priority entry is, but when we remove it, we have a tree without a root, and that's bad. We can't fall back to the algorithms we know for the binary tree deletion operation because the nodes aren't well sorted enough to find a successor. Instead, we're going to swap the root with the last entry of the array, the rightmost node of the last row of the tree. And then we're going to restore heap order. We call this process heapification, and sort of similar to how the insert operation went up the tree, heapification is going to go down the tree. We swap the root entry with the larger of the two child entries, and then repeat the same process with the newly swapped node. So 57 and 50. The larger of the two is 57, so now we'll have heap order for the first two levels. 57 will be greater than both 30 and 50. And then we're going to swap it with 52 and 42, I do believe. Note that it's a coincidence that we ended up swapping all the way through the very left side of the tree. Heap order doesn't impose any rules on how the value of the left child and the right child should relate to each other, only that they should both be less than the parent. So it would have been equally valid to have a tree with 50 here and 57 there. That would have still been heap order. Then we would have swapped there, and then swap there. And this is happily a good example because it shows that this operation is only supposed to go for as long as heap order is broken. After these two swaps, where 30 will be here, its child node, 28, is already smaller than the parent. Doing another swap at this point would break heap order, so we don't want to do that. As such, we stop when we see that heap order is already fulfilled. And since the entire rest of the heap was already in heap order. We know that the entire heap is in heap order once we fix that node we just moved. And just like the insert operation, this involves traversing a branch of the tree from the root to the leaf in its worst case. And since the longest path from the root to a leaf is in big O of log of n, where n is the number of nodes in the tree, the time complexity of retrieve max is big O of log of n. I want to take an aside. Not sure if this will work on my fancy new iPad, but we'll try it. I want to graph a couple of functions, just sort of like really drill it in that this is an amazingly cool innovation that both operations are in O of log n time. Okay, so far so good. So remember, if we implemented the priority queue using a normal old sorted array. Wait, which one was the fast one? I think we found last week that it would have been faster using an unsorted array. Just because adding a new entry to the priority queue would have taken constant time, just plop it at the end. And retrieving the maximum element would take linear time. Search through the entire array and return the largest item. Also shift anything else that's there. So, where did everything go? Also, if my explanations were unclear for how long the operations take on an unsorted array, put your hand up. I'll notice you eventually once I dig my head out of writing this stuff here. Okay, and now we're going to graph all these functions. And let's say the cost functions, of these operations, is like as good as it can be. This insert operation straight up takes one step. And the graph of its cost function looks like this. And then retrieve max for an unsorted array takes O of n. It's x and Desmos because notation rules for real numbers versus integers, whatever. And then for our log, we're going to use log base 2. just because that's what happens to come up most of the time in computer science. Plus, this is a binary tree. Its height is something log base 2 of the number of items. So that's probably an accurate picture of how long it's going to take. All right. So with an unsorted array, say you have 5 items, then inserting a new one is going to take 1 step, and retrieving the max is going to take 5 steps. And with a heap, both operations will take, we can round up to 3 steps. So if you want to do both, this is a nice coincidence. If you wanted to do an insert followed by a retrieve max, the unsorted array would take 1 plus 5, 6 steps. The heap would take 2.3 rounded up to 3 plus 2.3 rounded up to 3 equals 6-ish steps. So in this small example, they're basically equal, even though the heap already has a bit of an advantage. But let's say you're in the big leagues. You're programming a patient treating queue for a really popular hospital. You got 1,000 patients in the queue. Oh, I might have to make my example smaller so I can actually poke at it with the touchscreen. So with the unsorted array, insert would take 1 step, and retrieve max would take 1,000 steps. So if you wanted to do insert and then a retrieve max, that would take 1,001 steps. But with the heap, the insert would take 9.96. We can round that up to 10 steps. And the retrieve max would also take 10 steps. Doing an insert and a retrieve max, take 20 steps. So how fast would you prefer your computers to run at a hospital? It's sort of hard to understate just how much better logarithmic time complexity is over linear. We've got a difference in multiple orders of magnitude in how long these operations will take. It doesn't matter that the heap's insert is a bit slower than the unsorted array's insert. The heap's retrieve max is way, way, way faster than the array's retrieve max. Yeah?
So, I mean, we're not really doing stuff at this hospital that's more than, what, do you think, 20,000 people? I mean, you can get that in like a millisecond. Does it really matter at that point?
Wait.
Or this example, does it even matter?
Like, you're saying that since modern computers are so fast, like 1,000 steps isn't even that much? Yeah. That's true for my very brazen assumption that our linear function is exactly 1 times x or n or whatever, and that our log function is exactly log base 2, and our constant function is exactly 1. Literally any algorithm will take longer than those, and even when I insert really big constant multiples, the resulting functions will still have those stark differences in their asymptotic complexity. So let's say our constant time insert actually takes 100 steps. Our linear time, there we go, linear time insert actually takes 100 times x steps. And our logarithmic time heap operations also take 100 steps. So now our linear function shoots up so quickly that we can't even meaningfully compare them at 1,000. According to my calculations, it takes 100,000 steps, while the logarithmic one takes 1,000. So yeah, if the algorithms have cost functions as small as the ones that are in my example, the difference between 10 steps and 1,000 steps isn't really that significant. It'll lag by about a second. But with more elaborate algorithms, the kind, like, I'm not even going to say you'd see in the real world, more like the kind of algorithms that would exist anywhere outside of this contrived example, then you're talking about the difference between 1,000 steps and 100,000 steps, which sounds more like the difference between a few seconds and a few minutes, or an hour and a day, to complete some intensive operation. So yeah, logarithms are cool. If you find a O of log n algorithm for anything, you've kind of struck gold. So we're pretty much at the end of these slides. I think I'm going to do this exercise and then end the class, even if we're a couple minutes early. We're going to start from the heap below and draw the heap that results after calling retrieve max 3 times. We have all these patients in the hospital and we can treat 3 of them, I guess. Ooh, this might get messy. Oh well. We're going to delete the root and then replace it with the last node in the array, the rightmost node of the last row of the tree. And then we're going to swap it down the tree in order to maintain heap order. So 52 is the greatest of these 3 nodes. So we're going to swap it. And then, for the same reason, swap with 48. And then keep it there, since it's greater than both 20 and 25. All right, the heap is now once again in heap order, piece is restored, and now we want to retrieve max again. Take away 52, replace it with 25. And then move it down the heap, which will involve swapping it with 50 and then 45. one last time. We delete the root, replace it with the next or the last node of the tree. And move it down. So we swap it with 48. And then we swap it with 42. In both cases, we swap it with the greater of its two children, as long as one of the children is greater than the root. And then we check 30 is also greater than 20. 12 isn't. It's still out of heap order, and we need to swap it with 20. Or swap 20 and 30. And that's all there is to it. This is what the heap looks like after we've called retrieve max 3 times. So this kind of sort of ends this week's lectures, but as I discussed at the start of this class, we're going to start off next class by moving up to next week's discussion about heaps. We'll learn about another application of them besides priority queues. And then we'll go back to AVL trees from this week. All right, that's all. I'll see you all on Wednesday.